Welcome to This Explainer. It's so easy to just walk through the world and completely forget that the air around us is packed full of matter. It's constantly bumping into us, reacting, and, believe it or not, following some incredibly specific, elegant mathematical rules. So today, we are going to demystify exactly how gases behave.
Let's dive right in with a fundamental truth. Gas molecules actually have mass, and because they have mass, gravity pulls them down toward the Earth. Think about the massive column of air pressing down on us right now, stretching all the way from the surface of the Earth to the literal edge of space. That column exerts a very real 14.7 pounds of pressure on every single square inch of your body. We don't usually feel it, right? Because the pressure inside our bodies balances it out. But it is a massive, constant physical force.
Here is our roadmap for today. We're going to cover 4 key areas: the force of gas pressure, the 4 gas laws, the ideal gas law, and finally, gases and chemical reactions. All right, section 1, the force of gas pressure. Let's get our first building block in place. To really get what gas pressure is, think about the mathematical difference between force and pressure. Imagine an elephant and an ice skater. Now, obviously an elephant weighs vastly more than a person, which creates a massive downward force. But the elephant actually exerts less pressure on the ground than a tiny ice skater. Why? Well, it's because pressure is force divided by area. The skater's force is concentrated on this minuscule metal blade, which creates immense pressure. Meanwhile, the elephant's weight is distributed over 4 large, flat feet. Gas pressure works the exact same way. It's essentially the force of billions of microscopic molecular collisions distributed over a given surface area. And because scientists are measuring this force over area in so many wildly different contexts, from meteorology to aviation to chemistry labs, they end up using a variety of units. So we've got the standard IUPAC unit, which is the Pascal. We also have pounds per square inch, or PSI, which you probably recognize from your car tires. And then you have the atmosphere, where 1 atmosphere is exactly equal to normal sea level air pressure. And that's also perfectly equivalent to 760 torr. Moving right along to section 2, the 4 gas laws. Now that we know what pressure is, let's talk about the rules of gas behavior. What's totally wild is that your own body is literally proving Boyle's law every single time you take a breath. When you inhale, your diaphragm contracts and pulls downward. That expands your chest cavity, right? Which increases the volume of your lungs. Because that exact same amount of gas is suddenly in a larger space, the internal pressure drops. The higher atmospheric pressure outside then just pushes air right into your lungs to balance the whole thing out. And exhaling is just the exact reverse of that process. So, the crucial takeaway here is Robert Boyle's realization: volume and pressure have an inverse relationship. Squeeze a gas into half its volume, and its pressure doubles. But, and this is a big but, for this specific rule to mathematically work, you have to lock 2 other variables in place: the temperature of the gas and the number of moles, meaning the actual amount of gas must remain completely constant. Next up, we isolate temperature and pressure with Amintons' law. Just imagine a rigid, unchanging glass sphere connected to a pressure gauge. If we stick that sphere on a hot plate and crank up the thermal energy, the gas molecules inside start moving way faster. They're colliding with the walls harder and more frequently. Since the volume of the sphere absolutely cannot expand, that pressure gauge is going to immediately spike. Notice what we're doing here with strict variable isolation. We've completely locked down the volume and the amount of gas. This reveals a direct, linear relationship between temperature and pressure. But there's a vital catch you have to remember. The temperature has to be measured on the Kelvin scale. If you double the Kelvin temperature of a confined gas, you exactly double its pressure. Okay, moving on to Charles's law, named after the French balloon flight pioneer Jacques Charles. What happens if we hold pressure constant this time instead of volume? Just picture a sealed balloon placed inside a cold refrigerator. The cold gas molecules slow down, hitting the inside of the balloon with way less force. So to maintain a constant pressure with the outside room, the balloon's volume actually has to shrink. When you take it out, the gas warms up and the volume directly increases to match. Volume and Kelvin temperature just move right together. Finally, we've got the Italian scientist Amedeo Avogadro. Back in 1811, he advanced a hypothesis that actually looked at the amount of gas. Avogadro figured out that if pressure and temperature are fixed, simply pumping more gas molecules, which we measure in moles, into a flexible container will directly increase its volume. It's like blowing air into a flat tire. Add more gas, and the volume goes up. Which brings us to section 3, the ideal gas law. Time to combine the rules. We've rapidly gathered our 4 individual puzzle pieces: Boyle, Amontons, Charles, and Avogadro. Lining up their formulas side by side reveals something pretty fascinating. Each of these historical rules isolates just 2 variables while holding the rest constant. Boyle relates pressure and volume, Amontons relates pressure and temperature, Charles is volume and temperature, and Avogadro is volume and moles. This whole setup is practically begging for a unified mathematical theory to just bring them all together.
And when you smash all those distinct observations together, you get basically the master key of all chemistry, the ideal gas law. P times V equals N times R times T. Or pressure times volume equals the number of moles times a constant times the Kelvin temperature. If you know any 3 of the actual properties of a gas, say its pressure, volume, and temperature, you can use this one brilliantly simple equation to instantly calculate exactly how much gas you have. Now, you might be looking at that R and wondering what it is. Well, R is the universal gas constant. It's really just a number that perfectly balances our different units of measurement, making sure that atmospheres, liters, moles, and kelvins all speak the exact same mathematical language. But keep in mind, this equation assumes the gas is behaving ideally, meaning the molecules aren't crowding each other too much. It works absolutely beautifully at relatively low pressures and moderate temperatures.
All right, final section, gases in chemical reactions.
Armed with our unified master equation, let's step out of the physics realm and apply this directly to chemistry. Think about 3 balloons filled with helium, ammonia, and oxygen. These gases have vastly different chemical identities and molar masses. But as Avogadro's law tells us, if they are at the exact same temperature, pressure, and volume, they contain the exact same number of molecules, period. Oh, and as a quick aside regarding Dalton's law of partial pressures, if we were to somehow mix all these non-reacting gases into one single balloon, they would each exert their own individual partial pressure completely independently, and they just add up to the total pressure. This is honestly a huge shortcut for chemists. This profound realization from our source material means that when you're looking at a balanced chemical equation, like, say, 1 volume of nitrogen reacting with 3 volumes of hydrogen to make 2 volumes of ammonia, the ratios of the reacting gas volumes perfectly match their coefficients. You don't even have to weigh the gases. You can literally just measure their volumes to seamlessly track the stoichiometry of the reaction. As we wrap up this explainer, I want to leave you with kind of a wild thought. The math we covered today is incredibly neat and tidy. But remember, the ideal gas law requires ideal conditions, right? It needs polite gas molecules that are spread far apart and moving fast enough to just ignore each other. So what actually happens when you crush a gas under immense extreme pressure, or drop the temperature dangerously close to absolute zero? How chaotic do things get when real gases are pushed to absolute extremes and the rules of the ideal gas law just begin to break down? Well, that is a fantastic question to explore next time. Keep learning, keep questioning, and thanks so much for exploring with us today.